lesson 2.4, we're going to do trigonometry on a point on the coordinate plane. So we're going to be expanding our use of trigonometry to be not only with the geometric trigonometry of right triangles, but we're going to start to bring that to the coordinate plane so that we can build this system that's going to be really powerful. So we're expanding our idea of trig, and we're bringing it to this coordinate plane. So because of that, we're going to have to do some definitions and ideas and talk about what we mean when we say certain things. So we're going to start with an example. And that example is going to be using the coordinate point A, which we'll place at 3, 4. I'm going to do all 6 trig functions on this point. And so let's plot this point A. Let's say I go over 1, 2, 3 units and up 1, 2, 3, 4 units and land somewhere right around here. And we'll say this is A at 3, 4. Okay, if I want to do trigonometry on this point, well, you might notice that there's no triangle, and we've really been doing trigonometry with a right triangle. So I need to build a right triangle. So to actually do this trig, let's think of a list of steps that we have to do. So step 1 is going to be connect the point to the origin. Okay, I'm going to connect point A to the origin, which we recall is at 0, 0. This is going to be hypotenuse. This will be the hypotenuse of the right triangle we're about to build. Step 2 is to drop a perpendicular line or segment from A to the x-axis. So I'm going to draw a perpendicular down from A to my x-axis, and that will be at a right angle. This creates the right angle because we're trying to have a right triangle. And then step 3, we're going to complete the triangle using the x-axis as the third side. So I'm just going to complete my triangle here. Now, in this definition of trigonometry on the coordinate plane, we had to decide to build this triangle based on this point. So like this is something that we are choosing to define our system based on, and we're saying that if we have a point and we want to do trig on that point, we will draw the hypotenuse to the origin, drop a perpendicular to the x-axis. This forms our triangle. And then the angle that we're going to be interested in is going to be theta. Okay, so the angle is formed between the x and the hypotenuse. Okay, so consider theta between x-axis and hypotenuse. Let's put a big asterisk on this, okay? This is going to be a big asterisk. So we'll think of that for now as being okay, just to allow us to do some examples. But very soon we're going to realize that we kind of want to think of theta in a different way. But I think piecing it together right now, that's what we're going to want to think of theta as. So there's theta. So now we can do all our trig functions. I'm going to label the lengths of the sides of my triangle. So if the y-coordinate's 4 and the origin is 0, that means this length is 4. If x-coordinate is 3 and the x-coordinate of the origin is 0, then this length is 3. And then by Pythag, the hypotenuse is 5. So if I want to do my trig functions, I can say sine of theta, opposite over hypotenuse, would be 4 over 5. Cosine theta, adjacent to my angle theta, would be the side that's 3 over 5. Tangent of theta would be the opposite of theta over the adjacent of theta, which is going to be 4 over 3. So those are the 3 classic trig functions, and then we can use their reciprocal functions. Cosecant theta would be hypotenuse over opposite, or 5 over 4, the reciprocal to sine. secant theta is going to be 5 over 3, and cotangent of theta is going to be 3 over 4. And so these are the trig functions on the point A, 3, 4. And that's how we're defining this on the coordinate plane. Okay, and the only thing that's a little sketchy at the moment is this asterisk, considering that angle theta. For this triangle, it's actually perfectly fine because we're in quadrant 1. Maybe I'll give you a hint in the next one of how we might think of it in the future. But something else I want to show you is, say we picked the point B to be 6, 8, and I wanted to do all my trig functions on this point 6, 8. So let's move this out of the way a little bit. And let's say I went until I got to 6, maybe out here. And let's say 8 is somewhere up here. So we have 6, 8, point B. And if I wanted to do all my trig functions on B, well, B's side length would be 8, because that is the y length. The x length would be 6, and then by Pythag, the hypotenuse would be a length 10. So all my trig functions on B would end up being identical to the trig functions on A. We could say sine of theta would be equal to 8 over 10, but that reduces right back down to 4/5, which we saw just a moment ago when we calculated sine of theta on 3/4. And this should make sense because in our last video, I sort of hinted at the importance of similar triangles and triangles that have the same sort of angle that they're contained between, and this is the reason why. Cosine theta would be 6 over 10, but that reduces right back down to 3/5, so it is an equivalent ratio, and so on and so forth. So all those ratios will be the same between 6, 8, and 3, 4. So really the point of that is, if I build this angle here in standard position with an initial side and a terminal side, any trig function I do on any point on this terminal side will be the same no matter if the point's right here or way down here. No matter what, as long as I am on this angle theta, I am describing a specific ratio when I do trig on that angle. So that's a really important idea. Okay, let's look at another example then. We are going to go on to quadrant 2. So there's another concession we have to make to do trigonometry on the coordinate plane. And in this case, let's come over here. Okay, let's do trigonometry on some point C, which we will say is at -3, 3. So first things first, let me plot this point. Let's pull this over a little bit. Get it on the grid. Nice. Okay, so 3, -3. Actually, I want to extend this. So we'll extend, get a little extra space to work with. And I'm going to plot 3, -3. And now I can actually go, -3, 3. There's point C. Following my steps, to do trig on this point, I'm going to draw my hypotenuse. I'm going to drop a perpendicular to the x-axis, creating my right angle, and then the x-axis actually serves as my third side of the triangle. So I'm able to build my triangle. But here's the interesting part. In geometry, we would have said that a negative side length of a triangle was kind of ridiculous. How would a triangle or a shape have a negative side length? But now that we're on the coordinate plane, we can accept a negative side length. That's going to allow us to differentiate between this triangle -3, 3 and some other triangle with coordinate 3, 3, because these are describing somewhat different things. And so we accept negative side lengths to be okay. And so we would say that the length of this side is 3. The length of the side on the x-axis is -3. But we also are going to make a rule that the hypotenuse is always positive. And there'll be a more important reason for that later on, I suppose. If you do Pythag, if you say like 3 squared plus -3 squared equals c squared, you could make this argument 9 plus 9 is c squared, 18 is c squared, square root 18 is c. Ignoring the plus or minus, I'm only going to take the positive root here. and then that would simplify down to 3 root 2, which it ought to be because this is a 45, 45, 90 triangle. It's just got a negative side length, but the side lengths are the same magnitude, so we should have 3 square root 2 is our hypotenuse. Okay, so here's where this other asterisk I just talked about before came into play. We kind of think of this as theta, but technically theta is actually this angle, okay? This is the real theta, okay? Here's the real theta, because if we consider an angle in standard position, here's our initial side, here is our terminal side, and the angle theta is contained between those. So our angle is actually 135 degrees. The theta that we work with down here is called our reference angle. And so that is 45 degrees. That's the angle that our triangle sort of forms. And it's basically saying if we had drawn this triangle instead of right here, if we had drawn it in quadrant 1, that would be a 45-degree angle. And that would be true because our initial side would be here and our terminal side would be here, and that would be the angle formed. So, okay, that's a little something to understand. So technically, when we're doing all these trig functions using the point of -3, 3, we're actually doing sine of 135, and we're doing cosine of 135 if we do it in degrees, tan of 135. So all of this is going to be the answers that we actually get, and you can check that and confirm that on your calculator. But that's an important distinction because if you type in sine of 45, cosine of 45, and tan of 45, you might not be getting the right answers because we're actually describing the wrong angle. Anywho, if I'm using this real theta, right, to describe what we're doing here, and I want to do my trig, I can still just say it's the ratio of these parts of the triangle. This is how we're going to define things. So I'm going to say sine of theta is going to be equal to, let's get that reference, actually I'm going to do it in red just because, I don't know, I want to keep it simple. So we're going to say sine of theta, the red theta, 135, is equal to the opposite over the hypotenuse, 3 over 3 root 2. Okay, that's simple enough. That would reduce down to 1 over square root 2. Rationalize the denominator, we would get root 2 over 2. Reason being, we would multiply by root 2 over root 2, and yeah. So sine of theta should give us root 2 over root 2. Great. However, if we do cosine of theta, we're going to get -3 over 3 root 2. And this is where that's really important to have the reference angle. So this would be -1 over square root 2. Rationalizing is going to be negative root 2 over 2. And so I encourage you right now to go plug into your calculator cosine of 135 degrees, and I want you to type in cosine of 45 degrees. What you will find is cosine of 45, and make sure you're in degrees. If you're in radians, you would want to use, let's see, cosine pi over 4 for 45 degrees versus cosine of 3 pi over 4 for 135 degrees. And so if you compare these, if you're in radians, what you will find, and let me type it in, pi over 4 produces 0.7-ish, 1-ish. That's positive root 2 over 2. Cosine of 3 pi over 4, however, if you type that in, will produce approximately negative 0.71. So they're actually different because we're actually doing our trig on this angle theta, even though we're using this as our reference angle. So there's a similarity, but it ends up becoming negative. Okay. Going from that, we can keep doing the other trig functions. If I do tan theta, remembering that theta is technically 135, we're going to do tan of theta is equal to opposite over adjacent, so 3 over -3 equals -1. Very good. And I encourage you to put that in your calculator. Try tan 45 versus tan 135 if you're in degrees. If you're in radians, tan of pi over 4 versus tan of 3 pi over 4. Tan of 45, you should get 1. Tan of 135, you will get -1. So very similar, but not the same. And then this would be the same sort of set because it's just radians instead of degrees. Okay, so those are the classic trig functions. Then it's easy enough to just do the reciprocal ones. So we could do cosecant theta. Cosecant of 135 will be 2 over root 2, we could say. But actually, if we're just trying to do reciprocals, we can take this 1 over root 2 and just flip it, because that's already rationalized. So that'll be root 2 over 1, or just root 2. Likewise, when we do secant theta, remember that's the reciprocal of the cosine. We could look at the end product and flip it, or we could just look right here, an equivalent form, and just say that it's negative square root 2. And then finally, we could do cotangent of theta. -1, the reciprocal of -1 is still -1. Okay, cool. We will do 2 more examples, but this is really sort of starting to expand our definition of trigonometry onto the coordinate plane. And many of the different pieces we've been learning so far are starting to come together, and they're going to come together even more in a really, really important way soon. But for this lesson, this is what we're going to think about. So let's draw another coordinate grid, a little plane with some axes. Great. And let's do trigonometry on some point. Let's say D is the point. Let's do -1, -2. That's going to put us in quadrant 3. So I'm going to put D here, -1, -2. It's point D. By the way we define doing trig on this point, I'm going to draw the hypotenuse to the origin. I am going to drop a perpendicular to the x-axis, which in this case is now going up. And then the last side of my triangle is formed by the x-axis. Now, this is going to make my angle theta not that blue angle that I just drew. What do we call that blue angle? See if you can come up with it. That blue angle theta is called the reference angle, okay? Which is basically saying if we drew this same triangle in quadrant 1, meaning if we drew point 1, 2, we would have this same general triangle in quadrant 1. Look, you've even got vertical angles there to confirm it. That's what theta would be, the reference angle theta. However, theta itself is defined by taking the initial side here, right? And then we go all the way counterclockwise until we get to our terminal side through point D. So that is our actual angle. And this one I've picked random numbers, so I don't know how many degrees it is, but it's certainly more than 180. And then the reference angle would certainly be less than 90. And we can actually use inverse trig to figure out this angle, or we should be able to, but that might be a little advanced. Okay, let's label the sides of our triangle, and then let's do the trig functions on our point. Let's go dark blue. So this we said was 1. This is -2. By Pythag, we would have square root of 5, and the hypotenuse we always consider positive. So that's great. Therefore, sine of theta would be equal to opposite over hypotenuse, -2 over square root 5. If we want to rationalize this, we will end up with -2 square root 5 over 5. Cosine of theta is going to be equal to 1 over square root 5. Rationalizing gives us square root 5 over 5. Tangent of theta is defined as opposite over adjacent. And so we would say that that is -2 over 1, or just -2. So we get our set of ratios for the trig function. So we're able to do trig on this angle. recalling that this is the angle we're doing it on, even though we have a reference angle, theta. Yeah, so that's all good and well. Then we could do our reciprocal trig function, so I can do cosecant theta, and then I can just flip those upside down. Again, I could flip this, but why don't I look here? Because then I can just deal with not having to rationalize. So I get root 5 over 2, and it's negative. So that's good. Cosecant. Secant is the reciprocal cosine, so we get just root 5 over 1, which is just root 5. And then cotangent, we flip negative 2 over 1, and we get negative 1 over 2, or negative 1/2. And there we go. We've done 4 trig functions on a point. And note that I could have picked any scale of this point. So I could have said some point E is like -3, -6, because that would still fall somewhere out here on this green line and would still be using the same reference angle. Or I could have said -10, -20 and gone way out here, but I still would be falling on the same reference angle. One more example for you. We're going to go for quadrant 4. So we'll build our axes again. And this time I'll pick some angles that we might be able to more easily plug into the calculator. I'll pick a ratio that we presumably know. I guess that's going to be harder to do in practice. But let's say we have a point F, and we're going to say F is given by the coordinates, we'll say square root 3 and -1. Okay, and now I'm picking this because I know this comes from a 30, 60, 90 triangle. So square root 3 is about 1.7, so let's say it's somewhere out here. -1 we can say for sure is right about down here. And so if I put my point F here, I can say that it is at square root 3, -1. I draw my hypotenuse. I drop my perpendicular to the x-axis, which goes up, and then I complete my triangle. That gives me a right angle here. A right angle here. I also end up with a, what's the vocab word we use to describe this right here? That is the reference angle. Okay, so if we had instead chosen the coordinates in quadrant 1, say I'd said F was root 3, 1, if I had put it here, well then that would just straight up be theta, because then when I draw my angle in standard position, it contains theta. However, that is just our angle of reference to think about, because our actual, if I draw out my, let's pick a different color. If I draw out my initial side of my angle in standard position, and if I draw out my terminal side, and recall that we better be going clockwise, that is my actual angle. Okay, so that's something to bear in mind. Now, because I picked the coordinates that I did, we're going to have a angle theta, our reference angle theta, reference angle is going to be 30 degrees, or pi over 6 radians. My actual angle is going to be 330 degrees, or, what would that be in radians? 11 pi over 6 radians. Okay, and so that's going to be useful to test out later to just sort of build our repetition and understanding. Because the idea behind the reference angle is if we put it in quadrant 1, yeah, it's just 30 degrees, but here it's actually an angle all the way around of 330 degrees. Okay. All right, let's do our trig on point F. So filling in our triangle, we have square root 3 as our x, -1 is our y, and our hypotenuse is going to be +2 using Pythag or by using special right triangles. Okay, so then let's do sine. We said sine of our angle theta, and remember real theta is this theta that we're talking about, not the blue reference theta. So sine of theta is going to be equal to -1/2, opposite over hypotenuse. Cosine of theta is going to be equal to square root 3 over 2. And tangent of theta is going to be equal to -1 over root 3. Rationalizing, we would get negative root 3 over 3. Then if we go for our reciprocal trig functions, reciprocal of sine is cosecant theta. So we're just going to get -2 over 1, or -2. Secant theta is the reciprocal of cosine. We're going to get 2 over square root 3. Rationalizing is going to give us 2 square root 3 over 3. And cotangent of theta is going to be -3 over square root 3. So it's interesting, rationalizing we actually get negative square root 3. I suppose I can show that. We do -3 over root 3 times root 3 over root 3 equals -3 root 3 over 3, cancels, gives us negative root 3. I've got some practice, so I kind of just can do them a little faster, but yeah. All right, so that's all good and well. And so I want you to take your calculators. And I did try going into radians, or you can do degrees, whatever. Type in sine of 30 degrees or sine of pi over 6 radians. Guess what you're going to get? Positive 1/2, because your calculator is saying for this angle, 30 degrees, the ratio is 1 to 2. Now type in sine of 330 degrees or sine of 11 pi over 6 radians. And let's see what we get there. And I'll do that myself. 11 pi over 6. And we get -1/2, just as expected. And so on and so forth. You can test this with the other trig functions. But the idea here is that, like, the ability to change from 30 degrees to 330 degrees can somewhat be marked by a change in a positive ratio to a negative ratio. And that sort of represents that rather than being in this positive quadrant, we are now in this negative quadrant. What we'll notice too is in quadrant 1, we have positive, positive. Our x is positive, our y is positive. In quadrant 2, our x is positive and our y is negative. Oops, let's do it like this. Positive, negative, that's our x and our y. Notice the ratios that end up negative in our set. So our sine ratio and our cosecant ratio, which are ratios of the y-coordinate, basically. It is the y that is this negative side to the hypotenuse, which is always positive, comes out negative. It also is that our tangents become negative because we are comparing the ratios of our y side, negative, to our x side, positive. But our cosine ratios are positive because we are essentially comparing the x side, which is positive, to our hypotenuse, which is positive. So positive, positive is positive. So this is something to start thinking about. Overall, our main takeaway here is if we want to do trig on a point, if I put a point in the coordinate plane, let's try to improve our plane a little bit, a little askew. I put the point wherever it goes. Let's say it was here. I draw my hypotenuse and I drop a right angle, and then I can do trig using the coordinates to get side lengths and hypotenuse. But the idea behind it all goes back to angles in standard position of, oh, it's as if we have this angle extending, theta is here, but we build this little right triangle and we work with this right triangle because, like, our existing trig is right triangles. Trig is right triangles, right? So we're combining definitions and, like, building this system, and it takes some practice and getting used to, but these are some of the ideas behind it that we're going to start tackling. So hope this was useful. Hope you enjoyed the video. Thank you for watching.